So what is the source filter theory? So it was developed by a Swedish scientist named Gunnar Fant in 1960, and it is how the vocal tract filters the sound from the glottis. So the raw sound coming out of the glottis being filtered into what we know as speech. So this theory is based on a male's vocal tract for the schwa position, and they chose this because the cavities involved in speech production are roughly equivalent in volumes for this position. And there's three parts involved in the source filter theory, which are the glottal sound, which is the source function. The sound is sourced from the glottis. The vocal tract resonator, which is how the sound is filtered through the air cavities, which is the transfer function, and the sound that's coming out at the lips, which is the output function, which is what we actually hear. So these parts are all represented on different graphs. So this is the picture out of our book for the source filter theory. So the top graph is the source function, and you can see that the amplitude attenuates over time, and I think it's 12 decibels per octave. So yeah, and this graph shows the fundamental frequency, and the second graph is the transfer function. So you can see the spikes in amplitude that are the formants in the various air cavities in the vocal tract. And then the final graph is the output function, which is what we actually hear and perceive as speech. And this is the final product of the sound that came out of the glottis and how it was filtered through the air cavities and the vocal tract, and this is the final product. A particular range of frequencies, so energies outside of this are weakened or attenuated at a specific rate. And then the valves involved in the speech production are laryngeal, velopharyngeal, and labial. So the source function, which was the first graph that I talked about, represents the sound before it is modified, filtered, changed in any way. And it has the greatest amplitude. Like I said, the source function shows the fundamental frequency. And if you heard what this sound noise was like at this stage, it would be kind of like a low intensity buzz. And sound is sourced at the glottis, as I mentioned earlier. The transfer function was the second graph, and this graph is not representing a sound, but it's a resonance curve. So it represents the frequency response in the various air cavities. So when the sound moves through the vocal tract and goes into the different air cavities, this is the frequency response of that air cavity. You can see the spikes in the graph. And then the output function, which is the last graph, is showing what the sound is like when it emerges at the lips. So at this point, the glottal sound has been filtered based on the frequency response of the vocal tract. And this is what we actually hear as speech, or vowels, consonants, etc. So producing different sounds, various sound articulators are manipulated to create the different sounds that we hear. And the vocal tract is a quarter wave resonator because it's open at the lips and closed at the glottis. And as I mentioned earlier, the vocal tract is a band pass filter because it has three cavities: the oral cavity, nasal cavities, and the pharynx. And that's kind of like a series of air-filled containers that are connected to each other. And each has their own resonance frequency. And they respond differently when they're in different positions. And that's where you You see that on the resonance curves. So the irregular shape of the vocal tract and how it's easily manipulated, it makes it broadly tuned and able to transmit a wide array of frequencies. It has a wide bandwidth. So the vocal tract is a variable resonator, which means that the frequency response changes based on the shape. So when we move our speech articulators into different positions, it produces different sounds. The air cavities can change shape, volumes change, and then they resonate at different frequencies. So resonant frequencies, the vocal tract has many. It has a wide bandwidth, so it responds to a wide array of frequencies, but it responds best to the frequencies that are within that bandwidth. When we're talking about speech production, it's usually the first three formants that are considered. So when you move the tongue, it will either raise or lower the formants. The amplitudes of harmonics can be amplified or damped based on the shape of the vocal tract. So now that we know about the source filter theory, we can look at it a little closer during the production of a vowel. So I chose the vowel E, as in she or legal. So E is a front vowel. So going along with the source filter theory, we would first look at the source function, which is where sound is generated in the glottis through vibration. This would also show the fundamental frequency. And then we would look at the transfer function, which is where the articulators move into position for the E. Now this would look like lips being open and pulled back. The soft palate would be closed because there's no use of the nasal cavity. The tongue would be forward and towards the palate, and the pharyngeal cavity would be enlarged. So this would be showing where the formant spikes would be on the resonance curves when the articulators are moved into this particular positioning. Finally, there would be an output function graph to show the glottal sound that is coming out at the lips once it has been filtered through the vocal tract when the articulators were in position for E. So this graph, these graphs are from our book. So on the top left, you can see the source function that I mentioned. And then it shows the transfer function showing the formants or resonance frequencies for when the sound from the glottis goes through the different air cavities. And then lastly is the output function, and that's what the sound looks like when it comes out at the lips when it's been filtered through the entire vocal tract. And then the other picture on this is showing the tongue positioning in relation to the oral cavity and the pharyngeal for E. So now we can look at the source filter theory when producing a consonant. In this case, the production of the sound So is a bilabial nasal consonant. So again, there would be a sound emerging from the glottis from air vibration, and this would be represented with a source function graph. There would also be the fundamental frequency visible in this graph. And secondly, there would be a transfer function for when the articulators move into position for the sound. So since it is a bilabial consonant, the lips would be closed and the soft palate would be open because the nasal cavity is involved. So this would again be shown on the transfer function, and there would be spikes in the amplitude for the resonances in the various air cavities when the sound moves through the vocal tract. So there would be resonances in the oral and the nasal cavities. So then there would be an output function to show the sound when it is emerging at the lips. Yeah. So this picture is showing kind of a cross-sectional view of the vocal tract during the production of the sound mm. So as you can see, the lips are closed, the soft palate is open because is a nasal consonant, so the nasal cavity is being used. And then you can see the tongue positioning in the mouth. And you can see where the sound is coming from at the beginning of the vocal folds or the glottis.